Digital intelligence provides the logic for robotic movement, but without tactile perception, an autonomous system cannot adjust to the physical resistance it encounters. This sensory feedback converts digital instructions into successful physical manipulation. The World Economic Forum recently highlighted operational benchmarks for multimodal tactile perception arrays, demonstrating how direct contact and force feedback data enable higher precision in industrial and surgical robotics. In this tutorial, we will integrate and calibrate the XSense Tactile layer onto a robotic End-Effector, configuring the hardware to handle delicate objects safely. To complete this process, you will need the XSense sensor array, a micro torque wrench, and an edge compute control PC. By integrating this array, a standard robotic arm gains the precise environmental awareness required to operate as a highly sensitive instrument. Step 1 is securing the hardware. Begin by aligning the tactile pads directly onto the metal gripper plates. Insert the 4 mounting bolts. You need to tighten these in a diagonal, cross-pattern sequence to ensure an even distribution of pressure across the sensor face. Pay close attention to this hardware constraint. The bolts must be tightened to exactly 2.5 Newton meters. If you apply tension past 2.8 Newton meters, the localized pressure will physically warp the delicate mesh resting underneath the sensor pad. A warped mesh generates false positive phantom pressure data. The arm will register resistance before it ever makes contact with a target. Accurate digital output requires a perfect physical mount. Any unresolved structural stress at this stage guarantees software failure later in the pipeline. With the hardware securely mounted, connect the data tether and launch the control software to observe your raw, uncalibrated sensor feed. You will immediately see that the resting sensor arrays register microscopic, erratic readings. This is a standard reaction to ambient room temperature shifts and atmospheric pressure. To filter out this environmental noise, navigate to the system settings and execute the Calibrate baseline function. Looking at the monitor's telemetry, our primary metric is watching this jagged curve smooth into a perfectly flat baseline reading of exactly 0.00 newtons. Check the data across the entire spatial array. The maximum allowable variance must remain strictly capped at plus or minus 0.02 newtons. Establishing this mathematically pure zero baseline allows the AI to differentiate between meaningless background fluctuations and genuine, delicate physical contact. Cautionary: without calibrated force feedback limits, an automated hand applies full motor torque, swiftly crushing a fragile glass beaker long before the system realizes it hit resistance. To prevent hardware damage, access a force feedback settings in the Control API and prepare to input the system's safety guardrails. For handling delicate, medical-grade glass, configure your maximum grip threshold to exactly 0.45 newtons. Once the threshold is locked, we have to address the secondary metric, control loop latency. Open your edge compute performance monitors and verify that your system is keeping the polling latency under 10 milliseconds. If latency spikes above 15 milliseconds, it delays the mechanical braking commands. Even with your Newton limit set correctly, that brief delay will still crush the target object. With the pressure limits and latency constraints verified, initiate the final validation test by running the AI grouping script on a test file. Success is confirmed visually when the system dynamically halts the grip the exact millisecond the 0.45 Newton pressure threshold is met. Achieving strictly synchronized, low-latency tactile feedback separates primitive motor automation from highly functional physical AI. The physical mounting, baseline zeroing, and force feedback calibration sequences are now complete and successfully tested. Your robotic arm is currently processing direct physical contact using human-like tactile perception. The exact principles used in this baseline calibration scaled directly to high-stakes applications, including the precise movements required for delicate surgical robotics. Mastering the tactile intelligence layer provides the framework for advanced manipulation in environments that previously required human dexterity. Subscribe to AI Vanguard AI to stay at the cutting edge of industrial AI. If you found this synthesis valuable, please like, comment, and share.